A sphere of plutonium the size of a grapefruit holds enough energy to erase Manhattan from existence. We've all seen the mushroom clouds in the movies. We've heard the staggering numbers from Hiroshima and Nagasaki. Nuclear bombs are the ultimate modern-day nightmare. But here's the thing, most people have no idea how they actually work. We're cracking open the science behind humanity's most terrifying invention on this episode of The Infographic Show. For most of human history, we thought atoms were indestructible. The word atom literally comes from the Greek word for indivisible. Well, it turns out the Greeks were wrong. Spectacularly wrong. Atoms can absolutely be split apart or smashed together, and when they are, they release energy that makes TNT look like a tiny firecracker on the 4th of July. Here's where Einstein's E=mc² comes into play, but not in the abstract way that you learned in high school. That famous equation means that even just a tiny amount of matter contains absolutely staggering amounts of energy. How much? Just 0.04 ounces or 1 gram of matter, if completely converted to energy, equals the explosive power of 20,000 tons of TNT. That's enough to level several city blocks from something that weighs less than a paperclip. Nuclear fission is essentially the art of controlled atomic demolition. Certain heavy elements, like uranium-235 and plutonium-239, are naturally unstable. Their nuclei are just barely holding it together. When a neutron smacks into one of those unstable nuclei, it is game over. That nucleus splits into 2 smaller fragments, releasing a massive amount of energy. But that's not all. It also spits out 2 or 3 more neutrons. Those neutrons then go flying off and they hit other nearby nuclei, which split and release more neutrons, which hit more nuclei. It's like dominoes, except that each domino knocks down 2 or 3 more dominoes, and the whole thing accelerates exponentially. Scientists call this a chain reaction, and it is the beating heart of every nuclear weapon. But you can't just grab any random old chunk of uranium and expect it to explode. You need what's called critical mass, enough fissile material packed tightly enough that the neutrons are more likely to hit another nucleus than to escape off into space. If fission is about breaking atoms apart, fusion is about forcing them together. Take the lightest elements, hydrogen isotopes like deuterium and tritium, and then slam them together hard enough that they'll fuse into helium. The result is even more energy per gram than fission. There's just one tiny little problem. Fusion is what technically powers the sun. So in order to make fusion happen, you need temperatures of about 180 million degrees Fahrenheit and pressures that would make the bottom of the ocean feel like a gentle breeze. These are conditions inside the core of the sun, and recreating them on the Earth is, well, shall we just say, challenging. And that's why fusion bombs, also called hydrogen bombs or thermonuclear weapons, are actually 2-stage devices. The first stage is a fission bomb that creates the extreme conditions needed to ignite the fusion fuel. It's like using a stick of dynamite to light a much bigger stick of dynamite. Now that you understand the basic physics, let's talk about engineering. Building a nuclear weapon isn't just about getting some uranium or plutonium and then breaking it apart. It's about solving one of the most complex engineering challenges humans have ever attempted. You need to take a subcritical mass of fissile material and compress it into a supercritical state fast enough that it explodes instead of just fizzling out, which introduces another problem. Uranium-235 and plutonium-239 are constantly undergoing spontaneous fission, releasing neutrons randomly. In a subcritical mass, most of these neutrons escape without hitting another nucleus. The chain reaction sputters and it dies. But pack enough material together densely enough, achieve critical mass, and suddenly more neutrons are hitting nuclei than escaping. The reaction becomes self-sustaining. As we said before, for uranium-235 you need about 115 pounds for a bare critical mass. That's a sphere of about 6.7 inches across, smaller than a basketball. Plutonium-239 is even more efficient, only 22 pounds needed, about the size of a softball. When Little Boy was dropped on Hiroshima, it contained 141 pounds of uranium-235, but less than 2.2 pounds actually underwent fission. The rest was just along for the ride. The early bomb designers had 2 basic approaches, the gun-type design and the implosion-type design. The gun type was simpler. Basically, you fire one subcritical piece of uranium into another subcritical piece, you combine them into a supercritical mass, and then boom! And that's how Little Boy worked. But it was wildly inefficient and it only worked with uranium, not plutonium. The implosion design was far more elegant and became the template for virtually every nuclear weapon built since. And that's what we need to understand. Fat Man, the bomb dropped on Nagasaki, was a masterpiece of precision engineering disguised as a 10,000-pound steel ball. At its heart was a sphere of plutonium about the size of a softball, but that plutonium core was surrounded by a carefully designed system of conventional explosives that would compress it to supercritical density in a fraction of a second. The key innovation was something called explosive lenses, shaped charges arranged in a perfect shape around the plutonium core. These were precisely machined pieces of high explosive designed to focus their blast inward, like a lens focusing light. When detonated simultaneously, they created a perfectly spherical shockwave that compressed the plutonium core uniformly from all sides. The timing had to be absolutely perfect. We're talking about 32 separate explosive charges that had to detonate within 1 microsecond of each other, 1/1,000,000th of a second. Any significant timing error would create an asymmetrical compression. The plutonium would squirt out the sides, and instead of a nuclear explosion, you would get what bomb designers euphemistically call a fizzle. To put this timing precision in perspective, light travels at about 984 feet in 1 microsecond. The explosive charges in Fat Man had to be synchronized more precisely than it takes light to cross 3 football fields. When everything worked perfectly, the conventional explosives compressed the plutonium core to about 2.5 times its normal density. This was enough to push it well into the supercritical range, but you still needed one more component, a neutron source. This would guarantee the chain reaction would start at exactly the right moment. Even with perfect compression, you need neutrons to kick off the chain reaction at precisely the moment that the plutonium reaches maximum density. Too early in the reaction starts before full compression. Too late and the expanding explosion blows the material apart before the chain reaction can build up. Fat Man used a diabolically clever device called a neutron initiator, nicknamed the Urchin by the scientists at Los Alamos because of its spiky appearance. This hollow sphere about the size of a ping pong ball contained polonium-210 and beryllium-9 separated by a thin barrier. When the implosion wave crushed the Urchin, the polonium and beryllium mixed, producing a burst of neutrons right at the moment of peak compression. The numbers from here get mind-bending. Once the chain reaction began, it doubled every 10 nanoseconds, that is 10 billionths of a second. In less than 1 microsecond, the reaction went through about 80 generations of doubling. The temperature spiked, creating pressures that turned the plutonium core into an expanding ball of plasma. Fat Man released the equivalent energy of 21,000 tons of TNT from a core of plutonium about the size of a grapefruit. To put that into perspective, it would take a freight train 3 miles long, completely loaded with TNT, to equal the explosive power of that one small sphere of plutonium. By the early 1950s, scientists realized that fission bombs, devastating as they were, represented just the opening act. The real show was fusion, and the only way to create the extreme conditions needed for fusion was to use a fission bomb as a match to light an even bigger nuclear fire. A thermonuclear weapon, also called a hydrogen bomb or H-bomb, is essentially a fission bomb designed to destroy itself in the most productive way possible. It's a 2-stage device. The primary stage is a fission bomb similar to Fat Man, while the secondary stage contains fusion fuel that gets ignited by the primary. The genius is in how the 2 stages communicate. When the primary detonates, it doesn't just produce heat and blast, it produces an intense burst of X-rays. These X-rays travel at the speed of light and they reach the secondary stage before the slower-moving shockwave can blow everything apart. The X-rays get absorbed by a special foam casing around the secondary, which instantly vaporizes and creates its own intense pressure wave. This pressure wave compresses the fusion fuel while simultaneously heating it to the ridiculous temperatures needed for fusion to occur. It's like using one nuclear explosion to create the conditions for an even bigger nuclear explosion. The first successful hydrogen bomb test, called IV Mike, took place in 1952 on a Pacific atoll. The device was as big as a house and it required an entire building to contain its cryogenic cooling system for the liquid hydrogen fuel. When it detonated, it released 10.4 megatons of energy. That is 10.4 million tons of TNT equivalent, or about 500 times more powerful than Fat Man. The fireball was about 2 miles in diameter and completely vaporized the island that it was tested on, leaving behind a crater 164 feet deep and over a mile wide. The mushroom cloud rose 25 miles into the stratosphere. Ships 35 miles away recorded that the heat flash was still intense enough to cause third-degree burns. Modern hydrogen bombs don't use liquid hydrogen. That is far too bulky and complicated for a deliverable weapon. Instead, they use lithium deuteride, a solid compound that's much easier to handle and store. When neutrons from the fission primary hit the lithium, they convert it into tritium, which then fuses with the deuterium. Many hydrogen bombs also include a third stage, a uranium tamper or a casing around the fission fuel. The high-energy neutrons produced by fusion can actually cause even non-enriched uranium-238 to undergo fission. So you end up with a fission triggering fusion triggering more fission, like a nuclear chain reaction turducken. Unlike fission bombs, there's no theoretical upper limit to how powerful a fusion weapon can be. You just keep adding more fusion fuel. The largest nuclear weapon ever tested was the Soviet Union's Tsar Bomba in 1961, which released 57 megatons of energy. The fireball was 5 miles in diameter, the mushroom cloud reached 40 miles high, and the blast broke windows 560 miles away. The designers actually had to scale back the yield from their original 100 megaton design because they were worried about the fallout contaminating their own territory. The difference between a nuclear weapon and a very expensive paperweight comes down to the triggering mechanisms. Every component has to work with clockwork precision because nuclear explosions don't give you a second chance to get it right. The conventional explosives in a nuclear weapon aren't just there for show, they're the most precisely engineered explosives ever built. Each explosive lens in an implosion-type bomb is individually shaped and machined to create exactly the right pressure wave at exactly the right time. The explosives used are typically military-grade compounds like composition B or barytol, materials chosen not just for their power but for their consistency. The detonation wave needs to travel through each lens at exactly the same speed, which means the explosive density has to be uniform down to microscopic levels. Fat Man used 32 explosive lenses arranged in a soccer ball pattern around the plutonium core. Each lens was a complex three-dimensional shape designed using some of the most advanced mathematics of the 1940s. The whole system had to compress the plutonium core uniformly. Any asymmetry would cause the fissile material to squirt out sideways instead of reaching critical density. The detonation sequence starts with multiple detonators firing simultaneously. These aren't simple blasting caps, they are precision-timed devices that can be synchronized to within microseconds. In modern weapons, this timing is controlled by sophisticated electronic systems that can adjust for temperature, altitude, and other environmental factors. Having perfectly compressed fissile material is useless if you can't start the chain reaction at exactly the right moment. And that's where neutron initiators come in, devices designed to flood the compressed core with neutrons precisely when it reaches peak density. The original Urchin design used in Fat Man was ingenious but crude. Modern weapons use more sophisticated approaches, like tritium gas boost systems. These inject tritium gas into the compressed fissile material, where it undergoes fusion reactions that produce lots of neutrons. It's a small-scale fusion reaction designed to enhance a fission reaction that will then trigger a much larger fusion reaction in the secondary stage. Some modern designs use external neutron generators, basically small particle accelerators that can produce neutron bursts on command. These systems give weapon designers much more control over exactly when and where the chain reaction begins. Today's nuclear weapons are marvels of miniaturization and efficiency. A modern W-87 warhead weighs about 600 pounds and it's roughly the size of a large suitcase, but it can produce a 300 kiloton explosion, 15 times more powerful than the bomb that destroyed Hiroshima. This efficiency comes from decades of improvements in design. Boosted fission weapons use small amounts of fusion fuel to enhance the fission reaction. Two-point implosion systems use just 2 explosive lenses instead of 32, making the weapon smaller and lighter. Advanced materials and computer modeling have optimized every component for maximum yield with minimum weight. Modern weapons also include sophisticated safety systems. Permissive action links, or PALs, are electronic locks that prevent unauthorized detonation. Environmental sensing devices ensure the weapon will only arm under specific conditions, like the acceleration profile of a ballistic missile or the altitude and speed readings consistent with an aircraft delivery. Now it's the time to talk about the big boom. When a nuclear weapon detonates, it unleashes forces that were previously confined to the cores of stars. When a bomb achieves criticality, the fissile material begins converting to energy at an almost incomprehensible rate. Within the first microsecond, temperatures reach 180 million degrees Fahrenheit, 7 times hotter than the core of the Sun. The weapon's casing, the surrounding air, everything within hundreds of feet instantly becomes plasma. This creates a fireball that expands at thousands of miles per hour, For a weapon the size of the Hiroshima bomb, the fireball reaches 900 feet in diameter within the first second. The surface temperature is still 7,000 degrees Fahrenheit, as hot as the surface of the sun, and it's pumping out thermal radiation at the speed of light. This thermal pulse is actually the first thing that reaches targets at a distance. People and objects miles away experience the heat flash before they hear the sound or feel the blast of the wave. In Hiroshima, people within 2 miles of ground zero received third-degree burns from thermal radiation alone. The heat was intense enough to burn shadows into concrete and vaporize people close to ground zero, leaving only their silhouettes on walls and pavement. Following close behind the thermal pulse comes the blast wave, a wall of compressed air traveling at supersonic speeds. The overpressure from this shock wave is what actually destroys most buildings. At 5 pounds per square inch of overpressure, most residential buildings collapse. At 10 psi, reinforced concrete structures fail. The blast wave from the Hiroshima bomb created overpressure of 15 psi out to a radius of half a mile. The immediate effects of a nuclear explosion fall into 3 categories, each deadly in its own way. Thermal radiation accounts for about 35% of a nuclear weapon's energy output. This isn't just heat, it's electromagnetic radiation across the entire spectrum, from infrared to X-rays. The thermal effects are graded by a distance from ground zero. Within half a mile of a Hiroshima-sized explosion, the thermal radiation is intense enough to cause third-degree burns and ignite virtually any combustible material. Paper ignites out to 2 miles, dry leaves out to 3 miles. People caught in the open can suffer severe burns at distances up to 5 miles. The blast effects come from the shock wave that follows the thermal pulse by several seconds. This pressure wave is what does most of the structural damage. Buildings don't just collapse, they get crushed, twisted, and hurled around like toys. The blast wave also creates powerful winds that can reach 600 miles per hour near ground zero, hurling debris at lethal velocities. But perhaps the most insidious immediate effect is the initial nuclear radiation. A few neutrons are created and gamma rays are released by the fission reactions. This invisible killer can deliver lethal doses of radiation to people miles away from the explosion. In Hiroshima, people within half a mile who somehow survived the heat and the blast often died within days or weeks from acute radiation syndrome. The casualty breakdown from Hiroshima illustrates the multiple ways nuclear weapons kill. About 60% of the deaths were from burns, both thermal and from fires started by the explosion, 30% from injuries caused by the blast wave and flying debris, and 10% from immediate radiation exposure. The immediate effects of a nuclear explosion are horrific enough, but the long-term consequences stretch across decades. Radioactive fallout, the residue of fission reactions, gets swept up into the mushroom cloud and then scattered by winds across hundreds or thousands of square miles. This fallout contains a cocktail of radioactive isotopes with various half-lives. Iodine-131 has a half-life of 8 days and concentrates in the thyroid, causing cancer years later. Cesium-137 has a half-life of 30 years and mimics potassium in the body, irradiating tissue for decades. Strontium-90, with a 28-year half-life, acts like calcium and gets incorporated into bones and teeth. To put the radiation effects into perspective, the Chernobyl nuclear accident released about 400 times more radioactive cesium than the Hiroshima bomb. The area around Chernobyl will remain significantly contaminated for centuries. Cancer rates in the affected regions are still elevated more than 30 years later, and genetic effects are being detected in children born to exposed parents. Nuclear weapons testing has given us grim data on these long-term effects. The residents of the Marshall Islands, downwind from numerous hydrogen bomb tests in the 1950s, experienced elevated rates of thyroid cancer, leukemia, and birth defects for generations. Some islands remain uninhabitable due to residual contamination. Modern nuclear weapons are not only more powerful than their predecessors, they're also smaller, lighter, and more reliable. The engineering advances that have made smartphones possible have also made nuclear weapons more portable and precise. This should not be comforting in any way. The miniaturization means that delivery systems can carry multiple warheads. A single Minuteman III missile can carry 3 W-78 warheads, each capable of destroying a major city. The missiles themselves are so accurate that they can land within 400 feet of their intended target after flying 6,000 miles. Submarine-launched ballistic missiles are even more capable. A single Ohio-class submarine carries 24 Trident II missiles, each loaded with up to 8 warheads. That is 192 thermonuclear warheads on one submarine. each warhead roughly 8 times more powerful than the Hiroshima bomb. One submarine crew has more destructive power at their fingertips than all the explosives used by all sides during World War II. The global nuclear arsenal currently includes more than 12,000 nuclear warheads, about 9,600 of those actively deployed and ready for immediate use. The United States and Russia possesses about 90% of these weapons, with the remainder spread among 7 other nuclear-armed nations, plus one very likely nuclear-equipped Israel. To put this into perspective, all the explosives used during World War II, every bomb dropped, every artillery shell fired, every grenade thrown, totaled roughly 3 megatons of TNT equivalent. A single Ohio-class submarine carries about 19.2 megatons of nuclear firepower. One submarine has more than 12 times the destructive power of the entire Second World War. The economic investment in these weapons is staggering. The Manhattan Project cost about $28 billion in today's dollars. The U.S. currently spends about $60 billion per year maintaining and modernizing its nuclear arsenal. Over the next 30 years, the U.S. plans to spend $1.7 trillion on nuclear weapons and their delivery systems. But perhaps the most sobering statistic is this. The nuclear weapons that exist today have a combined explosive yield of roughly 4,000 megatons. That's enough to kill every person on Earth several times over. We have built weapons capable of ending human civilization, and we've built enough of them to do it thoroughly. Now that you know how a nuclear bomb works, the real challenge is making it through the aftermath. Check out This Is How You Actually Survive a Nuclear Attack, or click on this video instead.